Hi guys, today we are going to be continuing with section 4.1. We'll be looking at another way that we can evaluate a polynomial function for a given value of x, and then we'll also identify or assess how we can determine the end behavior of a graph given the function. And so if you remember where we left off yesterday, we talked about direct substitution. Well, there's a second way that we can do the same thing, that we can evaluate a polynomial for a certain input, and that's using something called synthetic substitution. Now, synthetic substitution has a little bit of setup. The first thing we do is draw this sort of large, L-shaped outline, and we put our input value, -2, on the outside. Then on the inside, we line up our coefficients. So our first coefficient is 3. Our next one would be -1. Then notice we skip an x cubed and an x squared in our function. We go from x to the 4th to x. So we account for those using zeros. Then our x term had a coefficient of -5, and finally 10. So that's the setup. Now to actually do the synthetic substitution, we drop that first coefficient down, and then we just start a pattern of multiplying and adding. So -2 times 3 is -6. If we add straight down, we get -7. -2 times -7 is 14. If we add straight down, we get 14, 0 plus 14. -2 times 14 is -28. If we add straight down, we get -28. -2 times -28 is positive 56. When we add straight down, we get 51. And -2 times 51 is -102. If we add straight down, we get -92. And if you remember yesterday when we did direct substitution for this exact function, we found out that f of -2 was -92. So same outcome, just different method. Okay? Here in example 2, we're looking at x equals 4, and our coefficients are 5, 1, -4, 1. We don't need any zeros because every term is represented. If I drop this 5 down below, I get 20. 4 times 5 is 20, 21, 84, adds to 80. Then 320 adds to 321. So f of 4 is 321, which is also what we found yesterday. Same outcome, different method. Now, if you remember from our previous study of end behavior, remember we're looking at where the ends of our graph are going, and we use f of x to describe those ends. There are 4 different cases for end behavior, and they all have to do with the degree in the leading coefficient. If we have an even degree and a positive leading coefficient, an example of a polynomial function that fits that description would be, let's say, a 2x to the 4th minus 5. Okay, now what I'm going to do is I'm going to pull up Desmos and we'll sketch a quick sketch of that graph. So 2x to the 4th minus 5. Okay, you'll notice it looks kind of like a parabola with a point down here at -5. Just a quick sketch. Okay, what I want you to notice is 2 things. Our ends are going together, and that's the case for every even degree. Anytime your degree is even, your ends go in the same direction. Okay, then because it's a positive leading coefficient, in this case, they both go up. So when we define our end behavior, x always goes to negative and positive infinity. Remember, this is like the left side of our graph. This is the right side of our graph. Okay. And in this case, an even degree positive leading coefficient has 2 ends that both go up. Now if we switch and we have an even degree but a negative leading coefficient, okay, let's say -2x squared, for example. Okay, again, because it's even, both of our ends go in the same direction, and then because it's a negative leading coefficient, they both go down. x is always negative and positive infinity. Down, down. Okay, so even degree tells me they go together. That means that an odd degree, if you think of when two things are at odds, they're disagreeing, so they go in opposite directions. Odd degree means opposite directions. An example of a function with an odd degree but a positive leading coefficient could be 10x to the third minus 4, let's say. So 10x to the third minus 4. Okay, so we can see that we've got this point here. Then it goes up from there. Okay, x still goes to negative and positive infinity. And as we said earlier, they go in opposite directions. One end's going down, the other's going up. Now, because this is a positive leading coefficient, our line is going up from left to right. So on the left, it starts down at negative infinity over here. On the right, it starts up at positive infinity over there. Okay. Now, an odd degree with a negative leading coefficient, let's say f of x equals negative 2x to the fifth plus 3x squared minus 1. Just an example, negative 2x to the fifth plus 3x squared minus 1. Okay, so this looks like it takes a little hop and goes back down. Again, odd degree means opposite directions. Okay, but a negative leading coefficient means our line goes down from left to right. So we start up at positive infinity and end down at negative infinity, down here. Okay. Now, an application of this end behavior and these characteristics is that if we're given a graph, we can describe the function in terms of its degree and its leading coefficient. Okay, in this case, both of our ends go in the same direction. So that tells me, that I have an even degree. They both go up, so that means my leading coefficient is positive. Okay, over here, my ends go in the opposite direction, so that tells me I have an odd degree. Okay, and I go from up to down in a negative direction, so my leading coefficient must be negative. I also can describe the end behavior given a graph, right? It says describe the end behavior of the function based on its degree and leading coefficient. So we have an even degree, negative leading coefficient. Okay, that means my ends are going to go down, down. So when I describe this, both of my f of x values are going to go to negative infinity as x, as always, goes to negative infinity, or as x goes to positive infinity. Now in this example, 6x to the fifth, so I have an odd degree, so they're going to go in opposite directions, but a positive leading coefficient. So I'm going to go up from left to right. Okay, this means that my f of x, my first end, will be down at negative infinity, and my second end will be up at positive. Okay, this one is as x goes to negative infinity on the left, and as x goes to positive infinity on the right. Okay, your exit ticket today is a combination of some synthetic substitution from up here, and then some end behavior applications like these guys. Okay, let me know if you have any questions. Tomorrow's a practice day, and I hope you guys have a great weekend. Talk to you soon.